So I gave folks a couple of minutes. I saw the escalators were broken downstairs, which is never exciting for conference activities. But welcome. If you are here for DevOps for AI, you are in precisely the correct place. And I am Paige Bailey. So if you're not interested in learning more about machine learning or data science or best practices for dealing with them both, then I will not be offended if you flee out the door. I promise. And hopefully you've been enjoying Build so far. This is my first one, and it's been absolutely delightful. So with that, let's get started. So this talk is a variation of one that I've given a couple of times before, mostly because of personal frustrations. But it's about DevOps for data science, or alternately, why life sucks if you're a data scientist, why your life sucks if you have to work with us, and how DevOps can make everything a little bit easier and help us work a little bit better together. So to get a feel for the room, how many of you are machine learning practitioners or data scientists? Okay, we have some hands. How many people are DevOps practitioners? Okay, so about half and half. That's really interesting. So hopefully there are tools and best practices for both of us. I'll be starting with kind of a theory-based approach. So what machine learning actually is for folks who might be a little bit fuzzy. How machine learning projects are architected and how they're operationalized, and then also walk into some of the trips and struggles that most data scientists seem to have, because most of us don't really come from a software engineering background or a sysadmin background, and we don't really learn all of the software development lifecycle best practices that software engineers and developers have kind of ingrained, and they've seen the truth. And now it's time for data scientists to see it too. So I'm Dynamic Web Page via the Twitters. So if you feel the yearning to go and tweet things, then please use my handle. So part one: why data scientists get paid so well, or why we would like to get paid so well. And this is kind of an overview of artificial intelligence in general. So AI gets thrown around a lot now, especially in developer conferences and in terms of building functionality into products. But artificial intelligence, by a textbook definition, is really just any technique that enables computers to mimic human behavior. And if you go by that definition, AI has been around for a long time. Like ever since you were able to explicitly program if-else statements for a computer to, so you say hello to the computer, and then the computer responds back through the terminal, and you just have this iterative cycle. So that's been around for a while. And the components of neural networks, they've been around for a bit too. Machine learning, though, is a little bit different. And that's the ability to learn without being explicitly programmed. So what does that mean? Traditionally, in programming, you're tasked with data. So you have data, and you define rules on that data, or on those inputs, and then you get back some sort of expected output. And that means that a lot of the responsibility for software engineering is on the computer programmer, right? Like you are expected to be the all-controlling master who knows all the answers and can explicitly incorporate every single step of the process, every little bit of the recipe. Machine learning takes a completely different approach. So you have the data, you have what you expect to see as an output, and then you give those to the computer, and the computer gives you back the rules. So instead of you having to explicitly program everything into your software application, the computer does it for you, which is kind of awesome, right? And there are a couple of different methodologies for this. This is highly simplified. There's also another category called semi-supervised learning. But the two major categories of machine learning are supervised and unsupervised. Supervised is what you do if you already have tags for your data. So you already know the answers. You know that this picture is of a cat, this picture is of a dog, this person defaulted on their loan, that's an exoplanet, something of that nature. And you can either be predicting a category, so again, cats versus dogs, red versus blue, Republicans versus Democrats, or you can be predicting a numeric value. and that would be a regression task. And regression, just think of it, again, as predicting how many widgets you're going to sell in July of next year, or it's going to be 88 degrees tomorrow. So you're just trying to predict a numeric value as opposed to a discrete categorical value. Unsupervised learning is less fun because it's harder. It's a lot harder. There's actually a tweet recently that it's much better to hire an intern to tag data manually for a month and then do a supervised learning task than to spend 6 months trying to figure out clusters in an unsupervised task and build a terrible model. So unsupervised learning, you've probably seen it a lot in clustering. But the thing about clustering is that when you get into higher dimensional spaces, and think of higher dimensional spaces as just like a spreadsheet with a whole bunch of columns, right? It's really, really difficult to pick out where clusters should be. It's easy to spot them in 2 dimensions. It's easy to spot them in 3 dimensions. But when you start getting out into that higher dimensional space, it gets a little bit more difficult. So for all intents and purposes, most of the algorithms that you'll probably see and that you'll probably be working with are either classification or regression problems. So that's a lot of words on a screen and not really intuitive if you don't see an example. So let's try one, right? So say your boss comes to you with a CSV file, because it's always a CSV file. And he says, all right, we've got our customers.csv, and you work at a bank, and we know some things about them. We know their age, whether or not they have a job, whether or not they own a house, their credit rating, their education, and then whether or not they defaulted on a loan. So whether or not they paid us back the money that they owed us. And really, if you're my boss, all you care about is that last column, right? Like, did they pay me back my money or not? And ideally, you would like to be able to find the potential likelihood of a default from this potential new customer. So he's 35, he has a job, he doesn't own a house, he has bad credit, he did go to college. What is the likelihood that this guy is going to pay me back my money? So you could do something. You could set up a decision tree, which looks a little bit like this. And you have a question or a specific category at each node. You answer the question, and based on those answers, you kind of follow it through, and eventually you reach a decision node where you either grant someone a loan or you don't. And if we followed this through for that example I mentioned before, our person who's in his 30s, who doesn't have a house, who is educated, should be given a loan because there's a high likelihood, based on all of that historic data that we have, that that person will pay us back. So again, examples are great, much better to show code. So if you go to aka.ms/build42, because 42 is the best number, and then also because all the other lower numbers were taken, then you should be able to find this IPython notebook. So there's a lot of stuff in this repo. A lot of it is related to the TensorFlow workshop that I gave yesterday. But this is a decision tree model implemented in R. So who has seen Azure Notebooks before? Cool. So Azure Notebooks is an online implementation of Jupyter. Jupyter is an interactive programming environment for data scientists. So you can type in commands, you can run it in a variety of languages, and you can immediately get back a response. So you can see visualizations, you can play with data, you can manipulate it quite easily. Yes, so the link is aka.ms/build42. Excellent. And each one of the cells in this workbook is interactive. So if you double click, you can automatically edit it, and the syntax works the same as any of the programming kernels that you have loaded. You can also introduce Markdown into some of these cells, so they build really nice reports. The most often used use case that I had when working as a data scientist for Jupyter Notebooks is being able to export them as HTML. So you can export them in a variety of formats, PDFs, HTML, whatever. But it was great to be able to set up a job to just run the notebooks and all of the code inside. and then to generate an output that was then placed in a URL for business reports. So if one of the managers wanted to see metrics for the last month, all they would do is go to that particular URL, and the data analysis would be periodically refreshed because all of the connections to the data sources were live. So it was a really great way to generate dashboards for people to see that were kind of more dynamic than you would expect from a typical business dashboard. But for the first step we have here, we would bring in the CSV file. You can see it automatically displayed with 17 different variables. Some of them are factors, some of them are integers. And on these variables, on these columns in our data set, so just think of these as columns in a CSV file, that's what we will base our analysis on for that particular machine learning problem. So we bring in the values, we divide them up into test and training data sets. I don't recommend using 90% for training ever, but just for the purposes of this demo, that's what we're going to do. And then actually creating the model itself. So we had substantial amounts of code to understand our data, to bring it in, to get it into a state that we wanted to. But to actually build the model itself, it's very simplistic. It's actually one line of code, right? So you're saying here, train a model on everything except that last column, and then use that last column, which is the yeses or nos for when something defaults or not, as the data for the predictor. So we build it out, and then we see our summary of the model itself. So checking account balance, dependence, and this is just a less pretty version of that tree diagram that I showed you before. So each one of these branches would be one of the nodes, and less than or equal to 1, greater than 1, those are the decision boundaries. So you just follow it through, and you get the summary for the model. After that's done, you can evaluate performance, and we can see here that we got most of the data pretty well classified. So we had 13.9% error, which means that we're probably a little bit overfit. But the decision matrix looks pretty good. And you can see that our attribute usage, it makes kind of intuitive sense as well. So if somebody has a checking account balance that's negative, they're probably not going to have any money to pay us back, right? That makes intuitive sense. If you wanted to improve model performance, you could take a whole bunch of decision trees and add them together. And you do that by just introducing this new hyperparameter. Sorry, my screen is apparently diving around lots of ways that it wants to. But you introduce this new hyperparameter called trials. You run 10 trials, and it's basically the same sort of mentality as a Monte Carlo simulation. You add a whole bunch of models together, and it improves the performance of all of them collectively. More heads are better than one. And here you can see that our performance boost is a little bit better than what we had before. So it runs through all of the model's iterations, and we get a boost performance of, I think it's 3.4%. Yep. Awesome. So this is a very, very simplistic example of building a machine learning algorithm. And you would usually do it if you were a data scientist in either a Jupyter Notebook environment, or you would do it in PyCharm potentially, or you would do it in RStudio if you were more of an R-focused developer. But for the most part, you aren't using Visual Studio. You're using a very specialized tool for data science purposes, and you're pulling in data from a variety of sources. So here it's just a CSV. It might also be streaming sources and others. So if we go back to our slideshow, it's problematic in a lot of ways, though. So it sounds a little bit like magic that you're able to get such high predictive accuracy. So being able to adequately say, yes, these people are going to default on their loans or not with just 1,000 samples and just one algorithm and probably less than 10 lines of code. But it's a little bit trickier than that in actual practice. And it's because your data usually looks a little bit more like that, right? Like it's never in a standard format. It's usually, you have floats mixed in with integers. You have text values that aren't standardized. You have all caps versus lower cases. You have tons and tons of missing values. And data is never a fun space to play with. It also comes in a variety of sources. So you might have XML that you need to parse, or JSON, or you might have tables in a database, and nothing has a standard key, so you have to figure out what you should be using, as opposed to what's already been given to you. And then also, what about other features? So for the first instance, we were given a CSV file, but it didn't initially include this account information. And that was apparently the best trigger as to whether or not a person defaulted or not. So if that's the case, then you would have to go to your boss and say, I need additional data. There's some feature that I think should be incorporated into this model that I don't currently have, and I need to find a location for it, I need to find a golden source of truth for it, and I need to have a way to incorporate with the rest of my data sets. And also model building. We tried one iteration of one model with very little hyperparameter tuning, and we had great performance at the very beginning, but who's to say that you couldn't try something else and get much better accuracy? It's never straightforward to build a machine learning model. You go through lots and lots of iterations. You might want to try branching off of different nodes in the tree. You might want to try a support vector machine, or you might want to try logistic regression or something else. So it's very interactive, it's never straightforward, and it can be effective, but it's also best suited for well-defined, very specific tasks with alphanumeric data, where your data is in a great format and where you understand it pretty intimately. So machine learning, primary takeaway, you have to be conscientious of your data. It's best for alphanumeric data, and it's best on usually small data sets. And machine learning, like I said, it's been around for a long time. Like the vanilla machine learning packages that you see for Python and R, you would probably have seen very, very similar ones in your 90s textbook on data mining or machine learning. So that hasn't changed much since university. But the new buzzword, the new hotness, is deep learning. Right? And what is deep learning actually? And it's a subset of machine learning. So it's using deep neural networks, whereas machine learning was using things like I mentioned before, decision trees, support vector machines, kind of shallow neural networks. And deep learning is learning underlying features in data by using those neural networks. So how is it used? It's used in a variety of ways, mostly with images. So very dissimilar to the example that I showed you before. You're able to automatically detect any sort of entity within an image. So how many of you have played with cognitive services? Excellent. So they're awesome. I think they're very cool. And they're backed with deep neural networks. So we've had some sort of model that we've trained on top of, and we've packaged them up into a containerized service, and you can ping them you can ping them as a REST API. And the way that the custom services work for cognitive services is that you're building on top of these deep learning models that have already existed, that have been trained for weeks and sometimes months on millions of images. And you just get to add a couple of additional shallow layers on top of it. But they're incredibly effective, and they're really, really powerful. You can also do specialized people detection, right? So detecting specific entities in your images. You can train it against a corpus of all of your employees and be able to pick them out in video footage, right? You can even architect a system where you're grabbing, video footage from surveillance cameras. You only pluck out the frames that have OCR done. So you have a model based on the camera, and you just kind of wait for people faces to appear. And then whenever a people face appears, you send that to Azure to get classified as a potential employee. So you can architect really powerful solutions with just very straightforward deep learning algorithms. You can also do things like disease detection. So here I have an example of spotting a tumor in a lung. And this is done by simply just having two directories of images. One that's, you can call it whatever you want, but it's basically cancer and not cancer. And you point your algorithm at it, and it basically cycles through every single image and determines what constitutes a tumor without you having to do really much of anything. Deep learning removes a lot of the struggles that you have with feature engineering and machine learning. Because in machine learning, you have to decide what's important. You either have to have domain-specific knowledge, or you have to kind of think outside the box about what could be impacting your problem. But for deep learning, you throw the data, you throw in what it should be, and you get back the answers and the classifiers that you would expect. It's also great for text. So this is what happens when you throw every single Harry Potter book at a recurrent neural network. It gives you back Harry Potter and the portrait of what looked like a large pile of ash, which sounds reasonable, right? Like that's very similar to most of J.K. Rowling's books. But you can also do things like language understanding. So we saw great examples with some of our Lewis bots. There have been a lot of advances recently with TensorFlow in terms of being able to understand natural language, even with ums and uhs, and have your neural network respond with those similar speech patterns. And then for sound, you can do things like create music. Or you can have a drag and drop situation where you create a melody. For folks who are familiar with kind of music composition, you create a melody, and then all of a sudden you can click a drum or any other instrument and have other aspects of the song complement the initial melody that you created. You can also do things like speech to text or speech to speech. And we saw a great demo of that the first day when Harry Shum was speaking in Chinese and his colleague understood everything he was saying, even though he was deaf. So it's huge advances and really, really sort of complicated data transfer formats. So we've seen images, we've seen video, we've seen text, we've seen sound, and there are a whole lot more. So autonomous vehicles, being able to automatically spot other cars and other potential driving hazards, being able to do kind of artistic transcription or translation, so you get Starry Night juxtaposed on top of Mona Lisa. And then AlphaGo, which is two generative adversarial networks, which are two neural networks kind of pitted against each other, and finding out the strengths and the weaknesses of both until you get an optimized neural network that can power through and complete the game. So deep learning's become really popular very recently. And when I say recently, I mean like in the last 2 years, for a number of reasons. It's now more accurate than humans. So there was this guy named Andrej Karpathy who was a grad student at Stanford, and he basically sat in his dorm room and hand classified this image set of hundreds of thousands of images. So this poor guy was just sitting in his dorm, image popped up on his computer, that's a cat, that's a dog, that's a book, that's a cup, and that's all he did for like a month. But that's also one of his claims to fame. So Andrej Karpathy, who is now the head of data science at Tesla, he is the human benchmark for computer vision. So Andrej Karpathy was 95% accurate, so we just assume that humans are 95% accurate at image classification. But now neural networks are more accurate than he was at classifying those images. We're also better at doing translation. So being able to translate between Japanese and English, it's now more effective to do that with a deep neural network than with a human. Even with all of the nuances of language and speech and kind of cultural hinting, it's still easier to do that with a neural network. There's also a great anecdote, translate.google.com. It used to be a computer program, about 500,000 lines of code, very statistically focused, lots and lots of very specialized heuristics, so very specialized rules that dealt with these one-off cases. They took that 500,000 line program and they turned it into 500 lines of TensorFlow. And that's what runs it today, and it's much more effective. We also have much more specialized hardware. So FPGAs you heard about on Monday, and they're really cool. They're very speedy at inferencing, and they also allow you to do very, very effective training. TPUs, which are tensor processing units, are a kind of custom ASIC. So actually, you're burning an algorithm onto silicon to get the best possible performance. TPUs are mostly kind of specialized for TensorFlow, or TensorFlow-ish use cases. But you can use FPGAs for a variety of other frameworks and a lot of other algorithms. And then we also have lots and lots of data. So obviously, we're pulling in sensor data from everywhere. We have this wealth of information, and data is the fodder for neural networks and for deep learning. We also have wonderful open source frameworks, and I call out here TensorFlow especially because it was I think released 2.5 years ago. We've only had a couple of TensorFlow dev summits, and it's grown immensely. Tens of thousands of contributors, lots of quick starts and tutorials, and all with kind of the mentality of let's create this open source software ecosystem to make deep learning as straightforward and as developer friendly as possible. So just like you can code a machine learning algorithm in less than 10 lines, you can create a deep learning neural network in less than 10 lines as well. So getting started with artificial intelligence, you can either create your own model, and you can do that with a variety of things like TensorFlow, Cognitive Toolkit, Scikit-learn, and hundreds. The deep learning community kind of gives JavaScript a run for its money in how many frameworks we create. And they have not as good names, though. Like I think there was a lawnchair.js recently, and that's kind of awesome. But yes, it feels like there's a new deep learning framework every week. And you can also deploy somebody else's model. And that's just using cognitive services, or if you have ML Studio, create some sort of service that you can connect to. That's a much more straightforward way. But if you wanted to create your own model, it would go something like this. So you would have a use case. This is one we like to use a lot. You would have, for example, people working on an assembly line for circuit boards. Instead of having people there, you might want to be able to do kind of the detection of outliers, the detection of imprecisely connected chips with computer vision. So say this, right? Like this is automatically, this is obviously created the way that it should be. It's very securely fastened. It's a correctly placed chip. The chip has gone on vacation, right? It's no longer there. How would we go about identifying that this chip has been that it isn't placed where it should be in this system? So if this is the case, if your boss came to you and said, hey, software engineer, build me an application that automatically detects whether or not a chip has been placed correctly, immediately you would start thinking in terms of if-else statements. Like I could sample the space in the middle of this image. If I get back orange pixels, then I could say, that's incorrectly installed. If I don't see orange pixels, then obviously it's okay. So we're just going to go with that. Sample, orange pixels, we're good to go. And that works for that particular use case. But what about that one, right? Like that chip is obviously missing as well, but there are no orange pixels for you to sample. And in that case, like what would you actually do? So, and then you would start thinking about how many components there are on a circuit board actually, and that you would have to define custom logic for every single one of those components as to whether or not they've been installed correctly. And then you would get really sad or you would get really excited because job security. But like that is not an ideal situation for a human to kind of go through and determine what constitutes a correctly placed part versus not. So there are better ways. And there is an example of one that I can show you here. So let me dive over to another Jupyter notebook. And this is a way to solve that problem. So to use Python as part of a Jupyter notebook to determine passes or fails for specific components on that circuit board. If I start the notebook server, you can see that it's pinging a Linux machine that we have on Azure. I just click through and go Shift-Enter, 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 Shift-Enter to run the code. It comes through. And we look at the first image. Just to prove I'm not fibbing, I'll change it to that one. And then detect as to whether it's been installed correctly or not. Let's try it with the second one. So that second image, and it's been installed incorrectly. And if you wanted to see kind of what the neural network is seeing through each one of its layers, it looks something like that. So it's picking out edges, like low-level features, and then mid-level features, and then high-level features. But none of this is explicitly programmed by you. Your neural network is the only one that's picking out each and every single aspect of this process. And then you can monitor your accuracy over time. So maybe as you make minute changes in your data or minute changes in your algorithm, it gets better or it gets worse. And then once you get a performance that you're happy with, so 94% accuracy feels pretty good, we'll package this up in a Dockerized container with a schema.json to define inputs and outputs, and a Python script to initialize and run the model. And that's in a container. That's an artifact that's easy, or relatively easy, for a software application to connect to. And that's an ideal situation for a data science model, right? For a predictive model, you want it to be packaged up. So that's kind of the overarching data science process. That's what happens whenever somebody goes to a data scientist and says, hey, solve my problem. You grab data, you start thinking about it, you test out some algorithms, you train with some hyperparameters, and then you tune it as needed. And some popular machine learning packages, and scikit-learn for Python, Caret for R, and some deep learning frameworks, TensorFlow, MXNet, Cognitive Toolkit, and PyTorch are some examples. And then Keras is the developer-facing front end, or that you should be using if you're using TensorFlow. TensorFlow is excruciatingly painful to write. It's like, it's got a lot of boilerplate, and it looks incredibly unfriendly. And then all of those tools that I just mentioned, they're automatically installed on our data science and deep learning virtual machines. So if you provision one of these assets, which you can get started with for free on Azure, all of those tools that I just mentioned are already there for you to use. And what's more, all of the package management is taken care of as well as the driver configuration. So if you're using a deep learning virtual machine, the NVIDIA graphics card is ready for you to go with TensorFlow or MXNet or whatever you choose. So hopefully I've convinced you that creating your own model takes time, it takes data, it takes experience, and it takes a lot of hardware, as opposed to just using a cognitive service or using something that you've trained in ML Studio. So that's part one. Part two, why people who deal with data scientists are superheroes. Mostly it's because our code looks a lot like that, right? It's never well documented. You have a lot of data analysis components, which means that there are a lot of, it feels like unnecessary bracketing happening, especially if you're using pandas. Often there are like double brackets to indicate columns. And then you're usually cycling through and kind of doing lots of visualization steps in your Jupyter notebooks. So you do visualization steps, you might get some statistics, you try out a lot of different things, and that's just kind of the reality. If you've heard of the obfuscated C competition every year, I think that was floating around Hacker News a couple of days ago. This is almost feels kind of similar. And the naming conventions look like that too, right? So you might have like bad data test, or Friday just trying something out, or untitled IPython notebook 25, or something like that. The naming conventions are just atrocious. And also version control is never a thing either. Usually data scientists are kind of operating in localized environments without using Git or Subversion or anything similar. And that's not, obviously not an ideal situation. And it's really difficult to convince someone who's never worked in kind of a team environment of why version control would be important. Jupyter notebooks are also notoriously bad at version control. And it's one of the reasons why I love using Databricks notebooks, because they have much better version control processes. Also, the languages that your stack is in, JavaScript, HTML, C#, Objective-C, I get whatever, Java, that's not what we use. So it's usually Python, R, sometimes Julia, but mostly Python and R. And there's no real support in other languages for those machine learning frameworks. There was a new binding situation for TensorFlow announced recently called TensorFlow.js, which is very interesting. It actually, it has node bindings, which means you can leverage the GPU in your laptop in the browser to do training for deep learning neural networks. But for the most part, other than ML.NET, which was just announced, other than JavaScript, which was, or TensorFlow.js, which was just announced, there's not a whole bunch of support on the other language side. And then also for the tools that you use, there's Visual Studio, there's IntelliJ, there's whatever on the developer side. And then for data scientists, everything's in Jupyter Notebooks or Jupyter Lab or Databricks Notebooks, PyCharm, Spider, RStudio, MATLAB, something very visual that makes it very easy to connect to data sources and very simple to bring in the packages that you love to do the data analysis itself. And the list goes on, right? Like not really understanding security best practices for data, not really understanding what a test constitutes or why you would need one, not remembering to turn off virtual machines. I am super guilty of that. And then also asking for support on, maybe machines that aren't standard to your workplace. So lots and lots of struggle buses for people who are familiar with SDLC best practices, and data scientists. Often, they're not even co-located usually. Like they might be on a different floor. They maybe have never sat with the software engineering team, and they might not even know what kind of endpoint would be useful to have for an application. Usually data scientists' outputs are like a CSV file with a bunch of IDs and yes or no, or true, false, true, false, true, false, true, false. And it's really difficult to explain why that's a problem. Like you can't build an application on top of a CSV file. But try explaining that to people who are responsible for doing just the data analysis component, right? So part 3, DevOps. Why this is so impactful and why this is so potentially useful to this situation in particular. So usually, one doesn't simply deploy a model to production, right? Like, so friends don't let friends deploy models without an update strategy. I mentioned before that, you would go through the process of selecting an algorithm, training hyperparameters, deploying it as needed, but then you would also need to check it periodically, make sure that the accuracy is what you're expecting, make sure that the assessments that you're making make sense over time. If you are predicting how many Surface notebooks were sold in downtown Seattle on a Monday, it's probably different numbers on build day than on just some random Monday throughout the year, right? Or different numbers around Christmas time than some random time throughout the year. And you would need to understand historical data in order to incorporate that in. And so Visual Studio Team Services is very, very effective at doing all of the steps that I'm about to mention. But you can use whatever you'd like. Obviously, Visual Studio Team Services is very near and dear to all of our hearts. And I'll show you an example of it in a second. But for the most part, whatever tools you'd like to use, feel free to. So best practices, document each step in the data engineering process. And the data engineering can, again, be done with a variety of tools. So SQL Server often, pandas, the tidyverse tools if you're working with R. But every single script, every single bit of data engineering should be well documented. You should also ensure that your data scientists are writing tests, and these might not look like the tests that you would expect. They're often going to be checking the data that comes into a model to make sure it's consistent with the data formatting that you had to create the model itself. So making sure that the sampling rate is consistent. So if you're sampling every 1 second and it changes to every 3 seconds, you would need to retrain your model to incorporate that. Or if the type changes for your piece of data. Or if you suddenly have 5 additional categories instead of just 2 or 3, you would need to make those allowances in your model, and you would need to change things to reflect that. And then also ensure your data scientists are using version control. And again, I don't really care what that looks like. You can use the automatic version control in VSTS. You can use Git. You can use GitHub. I don't care. But make sure that they're using it, and make sure that you can see kind of the history of a model's creation over time. And then also ensure that your models are portable and scalable. So the ideal situation that I mentioned before packaging up a model with a schema.json for inputs and outputs, and then some kind of script to initialize and run it, and a container, that's ideal, and that's what we should all be kind of moving towards. There are a lot of tools for that. So Docker is obviously one choice, but there's also, you also have the ability to scale up models with Kubernetes and using AKS, and that's very powerful as well. And then you also need to set up a cadence for model and data refresh. So being able to retrain based on data, being able to update your model based on whatever business requirements you have. You also need to define which performance metrics you want to capture. So accuracy might be the best choice for you. You also might look at something like an F statistic, because accuracy isn't always the best answer. If you had a data set where 99% of your values were fine, and then just 1% were the values of interests, you could create a model that identifies everything as fine, and it would still be 99% accurate, but that's not really giving you any sort of insight into that 1% that you're interested in. So again, you can do things like F statistics, get area under the curve, do accuracy, and then also define security and compliance standards for data access. So if your people, if your data scientists are analyzing data, make sure that it's data that they should have access to, that was agreed to be used for that specific purpose, and that you also have allowances built in for GDPR compliance, if that's impactful to you. And then also define a schedule for decommissioning and shutting down hardware. So that's kind of the overview of all of those bullets, right? So documenting, version control, writing tests, making things portable, doing model and data refresh, model performance metrics, security and compliance, and decommissioning and turning off assets. And most importantly, understanding that all of this is a continuous process. So it's all CI/CD. It's not just a typical waterfall project where you create a model, you go about getting all of the artifacts done, you deploy it as like this happy model out in the world, and then you decommission assets. That's never the case. You're going to have to constantly make sure that the model is kept up to date. It's like any software application that you work with. So data science DevOps best practices, they're just DevOps best practices. So hopefully all of this kind of made intuitive sense, that nothing sounded unfamiliar. It's just now there are more things to apply DevOps best practices to. And if you want to learn more about artificial intelligence, if you have that inkling, those are some of the best examples I can give. So Andrew Ng's courses on Coursera, Introduction to Deep Learning from MIT OpenCourseWare. DataCamp is a fantastic source of modularized machine learning and data analysis. There are a lot of textbooks out there. And then also Kaggle is kind of an online machine learning competition platform that I highly recommend you go take a look at if you'd like to kind of battle your friends with those. But yes, so those are the recommended resources. Let's actually take a look at what a machine learning project looks like in VSTS. And there's no Jordan Edwards out in the audience, right? I don't see him. Cool. So I was supposed to have a co-presenter today who shall remain nameless. But this is kind of VSTS. So Visual Studio Team Services for folks who haven't seen it before. Who has seen it before? Excellent. So VSTS is kind of an online, or I think you can implement it locally as well. But it's a standardized repository for all of the code, all of the files that you're working on. You can track commits, pushes, and even build kind of project management logic into this solution. So it's a great place to set up checks for specific components of your application, to set up checks for deployments, and then also to set up notifications and logging strategies. And everything that I just mentioned before, VSTS would support. So for files, being able to make sure that all of the files that are used for data engineering are incorporated during every single model refresh, making sure that everything is documented. And then for build and release pipelines, being able to add definitions to get started to make sure that if accuracy isn't quite what you need it to be, being able to monitor that over time and be able to stop a build of an application if your model's not giving you the performance that you need. So that is kind of a whirlwind overview of what you would need to do as a data scientist or a deep learning practitioner. If you'd also like to see what the artifacts themselves kind of look like, let me pull up a virtual machine really quick. And also, if anybody has any questions, feel free to ask them. I'd be delighted to take them as we're pulling up the virtual machine environment. How many of you have seen, and you'll also find out what I was doing with my time, how many of you have seen a deep learning virtual machine before? A few? Okay, cool. So this is a Linux virtual machine running on Azure. It's pretty performant. It's enabled with a GPU that allows me to do kind of more rigorous deep learning best practices, but you can leverage CPU as well for most of the sources. And it comes with a variety of files. So if you go into the desktop or into kind of your home directory, you can see lots of different notebooks have automatically been added for many deep learning frameworks and then also machine learning frameworks. So if I go to deep learning tutorials, we have things on framework comparisons. We have things for LSTM and product detection from images. We have, let's see, there was something I saw just recently. Yeah, so we have 6 different architectures for neural networks in deep learning virtual machines, and all of these are just running in Jupyter notebooks, the same as what we saw before. I can also use something called TensorBoard, and I think I've already launched it, so I can pull up a terminal, and Firefox, because Linux, and it should be this guy. So this shows the performance of one of my neural networks over time. It's sort of a metrics dashboard for specific deep learning architecture. So you can see that the metadata that I'm grabbing is associated with accuracy, cross entropy, and some other performance metrics that I would probably want to log and track and check to make sure that my model is performing the way that it should. You can also see graphs. So this is kind of it's difficult to make out, but since this is a transfer learning model, we're doing a lot of very specific layer building on top of a much broader model. This is built on top of something called Inception v3, which was trained by Google on, I believe, 14 million images, and it took a week. But I was able to retrain a model in just about 6 minutes on Azure, which is pretty cool. And you can also see distributions of your data and histograms. And the histograms, I think, are some of the most fun for understanding model performance over time and whether or not you're accurately classifying. So ideally, I'm not sure if you can see it, but when you start with models, you have validation accuracy, you have training accuracy, which is usually very high, and then you have cross entropy, which you want to minimize over time. So you want to get it the lowest possible that you can get. With each of these steps, each of these epochs, as I cycle through data sets, you can see here it's like step 3860. So there were a whole heck of a lot of steps. You get your training accuracy still high, but your validation accuracy is also still high. And ideally, your entropy goes down as you keep retraining. And the final accuracy for this classifier was about 90, I think 8%, which is kind of remarkable for what I'm doing. Perfect. There's also, like I mentioned before, Jupyter Notebooks, Weka, which is kind of very similar to ML Studio. It's a drag and drop machine learning environment. And then also Spider, which is very similar to MATLAB in configuration. It's an interactive programming environment for Python for data scientists. And RStudio, which I love, it's kind of a one-stop shop for all of our development. And it has a lot of additional extensions to pull in data from a variety of sources, including cloud-based sources. So I think that's all. So I'd like to open up for questions, and also hopefully this was useful to folks in the audience to kind of get a flavor of what DevOps folks would be looking for data scientists, and what data scientists should be kind of training themselves to give to a DevOps practitioner. So thanks.